So, hello. Welcome to this theory session in biomechanical testing of bone and orthopedic implants. This is the English version. If you are capable of speaking German, I would strongly recommend to switch to the other movie. But for the rest of you, welcome to this second theory session. Today, we are looking into more practical aspects of the mechanical testing of bone and implants, and we will talk about the steps that need to be considered when planning such experiments. So a very important part is thinking about and designing boundary conditions and load cases. So this will be the biggest part for today. And this is needed for actually grab your sample and put it into the testing machine. So this is everything around the sample. Then for measuring physical quantities, we will talk briefly about sensors. The ones of you who studied mechanical engineering before and physics, I think you have also relevant lectures for this topic. So we'll go into this only briefly. Sample preparation. Sample preparation is also important, right? Because the sample usually has soft tissue around the bone, and you have to think about whether you would like to keep it or you dissect your sample in some way. But a reminder to this, sample preparation will be left out this year in this theory session here. Yeah? In my opinion, well, it's part of this workflow you see here, but there are so many different ways of sample preparation, and I would rather show you this in practice in the workshop in our lab. Okay, so imagine you have your sample mounted in your testing machine, you have all the sensors mounted, the sample is prepared, then you have to apply loading protocol. So how, what displacement, what force you apply on your sample. And you gather data, and after your experiment, you have to do the data evaluation to extract the properties you want to know of your sample. We start with boundary conditions. What are boundary conditions? Well, the boundary condition as a concept is really simple. You have a sample indicated here with this potato shape, and your sample has a boundary. That's the outer surface of your sample. And boundary conditions are conditions that you prescribe on the outside of your samples, on the outer surface. There are two different kinds of possible boundary conditions. Either you apply a stress on the surface of your sample, or you apply displacement boundary conditions. Yeah? This is indicated by these two sides here. So on the left you see stress boundary conditions. So on a certain area of the surface you apply surface stress. This is what you can do by pushing on it, pulling, shearing, whatever. On the other hand, you can prescribe displacement boundary conditions. That means that you set the displacement of the surface points of your sample. So indicated here. So this means that on this surface of the sample, the surface is locked in space. It cannot move. Yeah? So this displacement is set to 0 here. Whereas down here on the lower right side, you see different kind of displacement boundary conditions. Here, this point here, well, in reality, there are no points. It's always, even if it is really small, you only have area. Yeah, so this is some small area here that is gripped by this bearing, by this slider, and this can move in this direction, but not perpendicular. So not in this direction. And this is also a type of displacement boundary conditions. That means displacements in these directions are 0, and displacements in this direction are open, yeah, are free. You can also prescribe displacements on the boundary. That means that you grab an area and you displace it, you move it in space across time, yeah, with a certain rate. You move it through space at a certain trajectory. So these are the two kinds of boundary conditions. When we consider boundary conditions for our mechanical tests, we have to think about first what we would like to measure. I introduced the concept of material properties and structural properties the last time, and this is something you have to decide beforehand before you design your boundary conditions. So first, we would like to look into boundary conditions to make tests on the material level. That means we would like to measure material properties like Young's modulus, yield stress, or ultimate stress. And we do this in the space of stress and strain. Yeah? So for determining material properties, we need to know the stress and the strain over time. Yeah? So we have to make those two quantities visible. So this is written here in more detail. So the goal here for the first type of boundary conditions for the material level, we would like to determine material properties, and we have to create boundary conditions to be able to test for specific material properties. This prerequisite here, it says we assume orthotropic material symmetry here, valid for both biological tissues. I wrote this sentence here because in the next slides we have to dig a little bit into the relationship between stresses and strains in your sample, and it is actually necessary to think about what your material does in terms of its symmetry. So there are different kinds of material symmetries in nature. Yeah? So maybe you have heard already about isotropic material properties. So this is the case when you have that's not a good example. If you have a material, yeah, and it does not matter in which direction you do your mechanical test, you will always get the same stiffness, for example, the same Young's modulus. So it's regardless of your testing direction in the material, you get the same number, and this means you have isotropic material properties. In nature, however, especially when it comes to biological tissue, this is not so easy, because depending in which direction you do your mechanical test, you will get different properties. So imagine you have a volume of bone, of trabecular bone, and you see it is made of struts, yeah, of bone bridges and bone struts, and they have a preferred orientation. So if this is maybe the axial direction of that larger bone, yeah, these small struts have a preferred direction, and that means if you do the test in this direction, yeah, then you will get different properties when you compare it to this direction or this direction. And this means it's non-isotropic. In general, you would say it's anisotropic, but an anisotropic material is really complicated. You have many parameters here. So usually you make an assumption to simplify the situation a bit. Yeah? And we do this here by saying, okay, our biological tissue, we would like to determine our material properties, is orthotropic in nature. What does that mean? That means you have three preferred directions. Yeah? So our material we are considering here has different properties in 3 directions. So you have a Young's modulus in this direction, you have a Young's modulus in this direction, a Young's modulus in this direction. And this is quite applicable for most of the biological tissues. And this is something you should keep in mind, that generally biological tissues are non-isotropic, and you can simplify, well, you have to consider them as being orthotropic. So 3 different stiffnesses in the 3 directions. So keep this in mind. Okay, so let's again. These slides describe now what is happening within our potato sample. So imagine you have a potato, you have mounted it somehow with displacement boundary conditions, and you apply stress here. Yeah? Then you will have a distribution of stress and strain within the sample. And if you zoom in and look into a certain material point, as it is shown here, you can describe the stress and strain state in this specific location with these 2 vectors, with a vector of stress components and a vector of strain components. So in each of those vectors you have 6 different numbers. So this is the stress in X, Y, and Z direction, and you have the shear stresses here, and the same is true for the strain components. You have strain in X, Y, and Z direction, and also the shear strains. And these numbers are changing when you move through the sample. So it's a very complicated state actually the sample is in. You have in every point of your sample 12 numbers, yeah, 6 for stress, 6 for strain, and they are changing depending on location. And in general, yeah, for this generally shaped potato sample, all these components are different to 0. So now we look into the linear elastic material law. This is also called Hooke's law. This is a matrix, basically, you see it here in the middle, that is linking those 2 vectors we have seen before. Yeah. Specifically, the vector of strains, written down like this, is equal to this stiffness matrix times the vector of stresses. And within this matrix, you have the material properties. So this is actually the thing we would like to measure, to determine. And let's have a look. In the case of orthotropy, our stiffness matrix looks like this. And how many unknowns do we have here? So we have a Young's modulus in X, Y, and Z direction, and we have 3 shear moduli. These are already 6 different material properties, but not enough. We have, in addition to that, 3 different Poisson ratios. These are these nu here, yeah? So nu Yx, nu Zx, nu Zy. And you should know that these 2 numbers are equal because of symmetry reasons. So that means nu Yx is equal to nu Xy. These 2 numbers are equal, so we have in total 9 unknowns, 9 material properties for the linear elastic regime only when we talk about stiffness. So I'm explaining you this because to tell you what the problem is actually here. Yeah? So when you have a generally shaped sample like this potato, you load it somehow. You have a distribution of stress and strain, and the material properties are hidden deeply in there, yeah, and also in a way that makes it actually impossible to determine them, even if you know the stress and strain state at a certain point. So imagine you have some glass sphere, you look in there as a Glaskugel, and you get to know the vector of stresses and strains at a certain point of your sample. So you would know these 12 numbers here, and you think, wow, now I can get my orthotropic stiffness values. No, you can't. You cannot. Because if you write that down, what is happening here, so this matrix multiplication, you will get 6 equations, but you have 9 unknowns. How should this work? It's not working at all. So you cannot, even by knowing stress and strain at a certain point, you cannot extract the material properties of your biological tissue, your linear elastic material properties. So what do we have to do? We have to simplify the situation. So what is the strategy here to get those orthotropic material properties? You have to create a stress and strain state in our sample that is simple and known. So not only known, but also simpler, as shown before. So this is not simple. And we do that in our testing machine by shaping the sample accordingly. You see on the left side schematics of a uniaxial test. Yeah, you have clamps and you have in there a dog bone shaped sample. We call this dog bone because it's shaped like the classical dog bone the dogs have in their mouths in the comics. Yeah, and what is happening here? Yeah, so via the clamps, force is applied and the clamps are clamping a sample, so there's compression, stress. But then you have these shoulders here, and these shoulders are there to get rid of the complicated stress state in this clamping region. And in the end, you end up with a very clear stress state within the measurement region of your sample. So maybe it's going between the green lines here. Yeah. So let's imagine between the green lines, all the disturbances happening here in the clamping region are gone, and we have a clear stress state, an uniaxial stress state depicted also here on this box. And when we have a coordinate system, we can now write down the stress state in our vector form. Yeah, and you see all the components are 0 except the one in this direction. So in this case, we apply a force in Z direction. The material coordinate system is oriented like that. Yeah, and we have a value here, and all the other values are 0. And we can quantify this value. How can we do that? Well, we measure our force, we apply with the testing machine, and then we divide the force by the cross-section area of the sample. We know that, we can measure the cross-section area of the sample, and then we can calculate the stress. So we know that number actually. And this comes in handy when we look again into our linear elastic material law. So remember, we would like to determine the numbers in here, and now the situation is much simpler because this value is gone, this value is gone, this number is gone, this is gone, this is gone. Everything is 0 except this value. And when you do the maths here, then the situation gets simplified. You get 3 equations basically. You get 3 equations for 3 unknowns, and all the other things can be measured physically with sensors in your testing machine. So let's check what we can measure. We measured, as I explained before, the stress. This is known. Yeah, we can measure the strain in Z direction. Yeah, so this is the change in length of that measurement region. This is epsilon C. This can be measured with an extensometer or with optical devices. For the nus, so for the Poisson ratios, down here, we need also strains in the transverse directions. so in X and Y direction. This is a little bit more complicated to measure, but it can be done also optically or with an extensometer. And what is this? This is the amount of the sample getting thicker or thinner when you load it. Yeah, so this is the change in thickness of the sample. Let's write it down here. This is epsilon y, and in the other direction it's epsilon x. Yeah, so into these two directions give you epsilon x and epsilon y. Yeah, so that means this is known, this can be measured, this can be measured also here, and we can calculate the Young's modulus in Z direction and the Poisson ratios in that directions, right? We can get 3 material properties out of this uni-actual experiment. And this can be done equivalently in also the other 2 directions. So imagine your first experiment was cutting out a sample in the longitudinal direction of your bone shaft, for example. You get these 3 numbers, and then you do a second and a third experiment where you cut out your sample in the transverse direction here, in that transverse direction, and in that transverse direction. That means you do in sum 3 tests. And what you can get out of these 3 tests are the 3 Young's moduli. So this, and this, and you get the 3 Poisson ratios out of this. So you get 6 unknowns out of the 3 uni-actual tests. Good. Yeah. You ask now the question, what is with the shear moduli? I'm coming to that in a few minutes. But before that, let's have a look on a different kind of compression boundary conditions. So before we had a sample clamped with 2 clamps. Here we have only 2 plates. And in between the 2 plates we place our sample and we compress it. This is done quite often, and you think it's simpler, but it's actually it's simpler to do, but what is happening in the sample is much more complicated. Yeah? So I would say the boundary conditions are not 100% defined here. Why? Because you have edge effects. You see on the left side that the upper surface of your sample is in contact with the plate, but the lower surface of the sample is not totally in contact because it's a little bit inclined. These 2 surfaces are not completely parallel. What does that mean? So if you compress the sample here, then the sample is in contact first on the right side and only after a certain displacement on your left side. So this introduces an unhomogeneous and inhomogeneous stress state. And we would like to have a homogeneous stress state, yeah? Because we need to know the stress to calculate our material properties. And to know the stress, it must be homogeneous and easy and clean. And this is not completely the case here. Yeah? We have a stress distribution, an uneven distribution of stress. You can overcome this by create a setup like this, but it's already quite complicated. You have a ball here and an additional plate that can adapt to the surface of your sample. But even if you do that, you have an undefined friction at the 2 contact surfaces. So as explained before, when you press on the sample, the sample would like to expand. And also at the top and at the bottom surface, the sample would like to expand. But it can do that only partly because it's pressed on the metal plates. Yeah? So depending on the friction state here, the sample can expand or not, yeah? Or it expands partly. But at least you don't know what is happening there. That means in the region of the contact, you have also not a clear stress state. You have a stress that you don't know. And yeah, so this introduces an error then in your evaluation of the material properties. And the third problem here, when you test microstructural samples like this, then the load is introduced not on a distributed surface. No, it's introduced pointwise on your strut surfaces here. Yeah? And then it's distributed along the struts in your sample. And depending on the stiffness of those struts, yeah, the sample is not loaded homogeneously. Yeah? So maybe the struts on that side are very soft and the struts on that side are very stiff. Then here most of the load is introduced and going then maybe like this in a cone downward. Yeah? And this is also not an even distribution of stress. But yeah. Nevertheless, this can be done, yeah, doing compression tests like this because it's easy. I'm doing it currently with the meniscus samples in our lab because actually you cannot cut out complicated dog bone samples of some of biological materials. That's not possible. So here it's easy because you only need to do cylinders, yeah, to cut out cylinders of your sample. Yeah, if you remember back, we had an open question regarding our shear moduli. How can we get shear properties out of our sample? Well, I would like to introduce you a few methods. This is the so-called Orzipescu shear test. So in here you see a specimen that is shaped like that with a notch. And the specimen is clamped in a complicated setup that is sliding up and down with those bushings here. And you apply a force, and it's intuitively clear that you get a shear load here in this region. So when you zoom in a material point in this region here, then you have a shear stress on your material indicated by these small arrows here. Yeah? So shear is doing that. This is shear. It's not push or pull, it's shear. And when you know the force and the cross-section area, you actually know also the shear stress. And as before, the vector of stress components is then simplified to something like this, where there's only one value left and you know that value. When you then go into your material law, this is again simplified to one equation. Yeah, coming from this line here. And you know the shear stress. And when you do optical measurement or with other methods, you measure the shear strain, yeah, then you can calculate your shear modulus here, GYC. And in combination with, so you do that again 3 times. That's equivalently possible for all 3 directions, yeah, and then you get all 3 shear moduli. So when you do 3 shear tests and you do 3 uniaxial tension or compression tests, you can get all the 9 stiffness properties, all the 9 material properties for the orthotropic material symmetry. And then you have the 9 values you want to know. Yeah? So 6 experiments for 9 values. Yeah. As before, I would also like to show you different ways of doing shear tests. This is a different kind of setup. It's an Arcan shear test, and you have fixtures shaped in this, this half circle. Your specimen is glued here in the middle, and this is also a way to do that. And you can also measure shear properties via a torsion shear test. So the sample is the cylinder in the middle, you apply torsion, and then you have a distribution of shear stress in the cross-section area. But it's a distribution. It's going from 0 in the center to some shear value on the outer parameter. And yeah, why not? It can be also done, but I think it's quite uncommon for very heavily microstructured samples, in my opinion. But yeah, why not? Okay. Now we have seen, if we sum it up, ways of creating boundary conditions to measure material properties. And this is done by controlling the stress and strain state in the material. Yeah. And to simplify that, so that many numbers are 0, so many shear and many stress and strain components are 0, and only a very limited number or only one number in your stress and strain vector, not the strain vector necessarily, yeah, but the stress vector is unequal to 0, has some number, and the number is known. Okay, to explain this more in depth, I would like to show you now real experiments. And this is our first example study. This is a study where they would like to measure stiffness and strength of trabecular human bone. So bone like this. And in this sample, they took biopsies from the hip bone, from your iliac crest. So this is this borderline here, and you can feel that when you press on your hip, you can feel this border. And what actually can be done is to extract biopsies out of the living patient. It's a small incision and some kind of a biopsy extraction tool is used, and then you can get those samples out of the living patient. And I don't know if it was a living patient here or if it was donor specimens, but in the end they had many samples like this. So they had cylinders with a certain diameter and a certain length. And now the goal was to measure the stiffness and strength of that bone. How was this done? So on the left you see a sample here. This is the original sample, and the sample was embedded, so it was glued to plastic rods here, to clamp the rods, because the sample itself cannot be clamped, it's too fragile. So they added these yellow cylinders here and clamped them in the testing machine and applied some load. And the displacement between the yellow embeddings was measured very precisely with this thing here. This is an extensometer. An extensometer has two bridges or two beams, and they can move. So these are two beams, and they are attached to the sample. And when the sample is here, and when the sample is compressed, the two beams go like this, and this can be measured really precisely with a resolution of 1 micron, for example, 1/1000th of a millimeter. So the sample is compressed, and your two beams of the extensometer go like this. So the compression, so the strain of the sample can be measured with this extensometer. And the force is known, and when you divide the force by the cross-section area, which is also known here, you can get the stress. So let's have a look on the actual testing data. This is the cyan line here, the cyan color. And you have on the y-axis the actual stress, and on the x-axis the actual strain. And the test was started, going on and on and on. And then at some point the maximum stress was reached, and here the test was stopped. The thing when you do compression tests is actually the sample fracture is not indicated by drop of force to zero. No, you can imagine you do a compression test on this thing here, on this sample, and you compress it, yeah, you crush it. At some point maybe you reach a maximum stress, but then you have these fracture pieces in between your two plates, and you can apply even more pressure suddenly. Yeah, you are compressing the remainings of your sample, and you would get, when you are rather here and everything is compressed here, again an increase in stress. And this was avoided here by stopping the experiment. Yeah, so this was not a drop of stress. No, the experiment was stopped here at this point. Yeah, to avoid compressing the sample too much and again have a rise up of stress. Okay, so what can we now extract out of this experiment? We can get the Young's modulus of that sample in that particular direction. So remember, if the material is orthotropic, you would need to do 3 tests. And in this case, this was the Young's modulus of the selected direction of the sample. And that's the slope of that line here, of that regression line that is fitted to the linear elastic region, yeah, of the curve. Then, this is easy. That's the maximum stress measured. That's the ultimate strength. Yeah, that's the point where the sample is degraded and getting mushy. Yeah. Okay, and these are the 2 material properties that can be extracted out of this experiment. Young's modulus and ultimate strength for that particular direction, for that particular sample. Second study, shear tests on cortical bone. Cortical bone is the hard and compact bone on the in the shaft and also on the outer surface of the joint regions. And the scientists here would like to determine the shear modulus depending on the sample orientation. Yeah, so you see the shaft here, and they cut out samples in different directions, and then they do shear tests. So this is the Isopescu shear test, as explained as the first shear test in this presentation. The sample is clamped here. This piece is fixed, and the right piece can move up and down. Here you see a pin that slides in and out of this base plate. And by looking with the camera on the surface and by applying DIC measurement, the shear strain can be also measured along with the stress. Specimens used here with human femoral bone. And the deformation measurement was done with digital image correlation, so with the camera basically. How this is working and what is meant by that will be explained later in the sensors section. Okay, and the outcome was first load and displacement. So these are the original values usually you get. You get directly the force out of your load cell and the displacement of your machine. And you see the different load displacement characteristics depending on the angle at which the sample was extracted from the bone. So then this is converted to shear stress by dividing it by the area in this measurement notch. And here you have the engineering shear strain expressed as the shear angle. So what the shear angle is explained here in this sketch. So this is how the sample is deforming in that way. Yeah, then an angle is opening up here, and this was measured with the camera system. Okay, and what can be extracted out of this experiment is you take the slope of the initial linear region, and the slope of that is the shear modulus. And it's the shear, so an increment in shear stress divided by the according increment in shear angle here. And as they extracted the sample in different directions, so 0, 30, 60, and 90, they can get the shear modulus for those different directions here. So this is 4 gigapascals, 3, 3.5, 3.5. Yeah? And yeah, and they know now the shear properties of their cortical bone samples. Okay, so this was a small and very compressed insight how to create boundary conditions to measure material properties. This was the more difficult part. Now we go into the second field, namely creating boundary conditions to measure structural properties. So instead of using stress and strain, we use force and displacement here, and we would like to measure not ultimate stress, but ultimate force, for example, for a certain sample. And these boundary conditions for structural properties, they depend strongly on a research question. I would like to raise the term of physiological boundary conditions here. I will go into this in a few seconds. And basically again, so you would like to measure stiffness and failure load, for example, of bone and bone implant constructs. Not Young's modulus anymore, not yield stress or ultimate stress. So nothing with stress, nothing with strain anymore. We are now in the force and displacement regime. And these are the usual properties we would like to determine: stiffness and failure load, or yield load. And these depend on the research question. At this point, I would like to introduce the term of physiological boundary conditions, because this is something you would like to achieve. What is this? Imagine your bone is inside your body. So the femur bone is below all these muscles here. It's attached with tendons and ligaments to your body. So it has a very complicated set of boundary conditions. There's soft tissue around it. There are some regions where force or displacements are introduced. And this is how it is in your body. And when you do an experiment of your bone, you would like to measure, for example, the fracture load of that bone. So when it breaks, you should consider doing that as closely as possible to the conditions if the bone was inside a human body, because then it's more representative to the real world, right? So it makes a difference if you, for example, break this bone like this. You would like to measure fracture load in that direction, and you can do that, of course, but it makes a difference whether this bone is covered with a lot of muscles and the muscles are exerting some force on the bone, or there's nothing. So it depends really on the research question, how closely you have to resemble the physiological boundary conditions. And the physiological boundary conditions are the boundary conditions in the human body. And in addition to that, for example, you would like to measure the fracture load of the bone in the case of a car accident. Then, when you consider a car accident, the person is sitting in the seat. So the bones have a certain alignment to each other. You have a certain excitation or activation state of the muscles. So the muscles are exerting defined force on the bone. And you have certain external loads coming from the car, so from the accident, on your bone. And these together gives and creates the physiological boundary conditions for this particular load case. But the point is, this is really complicated and actually impossible to do. Yeah, so things have to be simplified as much as possible without loosening the meaning, so the conclusion of your experiment. So this is physiological boundary conditions. Keep this in mind, please. Let's have an example research question. Yeah. So the idea is to determine the fracture load of the femur in the conditions of a side fall. So what happens here? You see the lady is ice skating. She's falling on her hip. That means she gets an impact like this on her trochanter. This is the trochanter here. Yeah. And usually what's happened then, the body load is transduced via the hip joint here on this neck. This is the neck region. And if this is a hard hit, yeah, the neck can break. Yeah, this is the classical hip fracture. I think that's the most abundant fracture on the world, or the second most, I don't know, first or second most fracture of the world. Yeah. Side fall, body weight crushes here. Yeah. Here's the bottom, the floor, and the neck breaks. And we would like to measure the fracture load for this particular load case. So how high can this load be for the bone to fracture? So when is the bone fracturing? And the strategy here is, as indicated before, it's a very complicated situation if you look on this lady. Yeah? So we need to make it as simple as possible to be able to reproduce the situation on our testing machine. So let's reduce the complexity. Yeah? You see here, this is the real situation. The force of the hip is introduced on a surface on the head of the femur. You have muscle forces exerted, and you can stepwise reduce the complexity by neglecting the muscle forces at all and introducing force at a certain point. And yeah, you can do that. And how do you check whether the simplification is valid? And here a certain strategy can be applied. So this is an actual study, yeah, an actual study done at the TU Vienna in our group. And here we wanted to measure this fracture load. And we needed to simplify the situation a lot to be able to do that in our testing machine. And the idea was to create boundary conditions so that the fracture pattern of the sample is similar to the clinical situation of real patients suffering this side fall and this hip fracture. So again, yeah, when a person falls to the side and goes to the hospital, then you have a certain fracture pattern here in this neck. And in our study, so in the study of Enrico Dallara, he was creating boundary conditions that gave exactly the same fracture pattern in the neck as in the clinical case. And in this case, it was sufficient to clamp the bone like this. So that you see that the bone was cut here, clamped here, and embedded at the trochanter to represent the floor, the impact on the floor. Yeah? And at the top, on the head, the body load was introduced by this cup here. Yeah? And the machine was pressing downward in this direction. And after some millimeters, the neck of the sample would break in exactly the same fashion as it would happen for an actual accident, an actual patient falling on the side. So we could say here that we created sufficient physiological boundary conditions for this particular research question. And you see there are no soft tissues around or any tendons or ligaments in place. Yeah. This was the strategy here. Okay, what else do we see on this picture? We see a load cell. So here the force was measured. You see a bearing here, because when you apply a force on the head, this piece would like to move also in a transverse direction. So to allow this, to not hold it in place, yeah, and to make the boundary conditions more clear, there was a bearing. So this lower piece here could slide left and right and back and forth freely. This makes sure that we had only a force really in the vertical direction, no other forces on the head. Then these things here with the small wires, these are optical markers that could measure the displacement of these points in 3D with an accuracy of around 20 to 30 microns. So a very precise optical measurement was applied here to track the displacement of all these different positions in space. Yeah, and then the bone was clamped here, the load was applied until fracture, and then it was unloaded. Let's have a look on the results. In this plot, I will show you plots of two samples. So this is sample number 1. Please only look on the red line here. Forget the other lines. Yeah, the other lines are simulations and different things. So the actual experiment on the real sample in side fault conditions is this X underline SI line. This is the red line. Yeah. And you see that so on the x-axis you have the displacement of the machine in millimeters, and on the y-axis you have the force measured in the load cell. And the test is starting here. The load is introduced. We go into the negative regime of values because we have a compression test. This is a convention. Yeah, you can also say it's positive, but in this case, so usually we say that compression is negative and tension is positive, but this is just a convention, a selection. Okay, so the load was rising until this value, slightly below 5,000 newtons. This was the maximum load, and then with further deformation the load was dropping. Here Enrico stopped with the machine, and then he started to unload. So moving up with the load introduction parts. And here the force was 0, but we had a remaining displacement. You see 2.5 millimeters at no load. Yeah? That means the sample was deformed plastically, so forever, 2.5 millimeters without any load anymore. So the sample was fractured. And the fracture load, the load of failure, was the maximum load here, slightly below 5,000 newtons. Also called the ultimate strength. This is the second sample. You see a great variation. So the second sample had approximately half the ultimate strength, but it's the same story here: load, maximum load, and then an unload situation. Yeah, that's it. This was the experiment for extracting the fracture load of human femoral necks. Classical fracture happening very, very, very often on the world. Second example, also shown by this lady. You see that the right hand of the lady is hitting the floor when she would like to stop her fall, and this can also produce a very common fracture, a distal radius fracture. So in there you have two bones, one is the radius, and when you have a hit like this, so for example for ice skating or snowboarding, you can fracture your radius in a very certain manner. So you see that on the X-ray here. So this is the fracture gap. Yeah, also there's the fracture gap also here. And this is a very, very abundant fracture. Also, that's either the first or the second most fracture on the world. This fracture has a name, it's the Cole's fracture. So Mr. Cole gave this fracture a name. So when you speak of the Cole's fracture, that's the one. And this one is often treated with a plate. So when you go to the hospital, then you have suffered from the fracture. You go to the hospital, and to align these two fracture pieces, so the shaft and the joint region has to be aligned in a certain way, so that after healing, your wrist is again functional. For this alignment, a plate is often used. Yeah, so bone implant construct is created here. Yeah, and you see a plate of a certain company here. These are the according X-rays. There are many screws screwed in. I have a sample of that. Actually, yeah, this is it. Yeah, this is the actual plate screwed in. You see the fracture gap, screws sticking out a bit on that side. And this is how it is treated in the hospital. And the question is here, so the patient goes in the hospital, has a surgery, has a plate like this, but it's still winter time. The patient is leaving the hospital and is falling again on the wrist. Yeah, is again falling on the wrist. What is the fracture load there after having an implantation of this plate? What is the fracture load of this bone implant construct? This is the research question we would like to answer. Is it higher of the original bone? Is it less of the original healthy bone? So we would like to quantify that. There a study was done also in our group. And two questions have to be answered here with the boundary conditions. So first, how to simulate a fall on the wrist. So this fall, yeah. How can I do this in the testing machine? How can I simulate this fall on the wrist? And it shows that when you embed the radius bone at the top, so in the joint region, with such kind of a wedge, yeah, you see it also here. It's a wedged shape embedding, and I also have it here in my hand, yeah. So this is not even, it's a wedge, and when you do that and you press on a full radius bone, you have again the same fracture pattern as you have in clinics. When patients come to the clinic and have an X-ray, yeah, you get the same fracture, a Cole's fracture, when you have embeddings like this. Okay, this was the first question. So what boundary conditions to simulate the fall? The second question is how to simulate an already fractured bone. So we are testing here a fractured bone with an implant. So we need to create the fracture artificially and then screw in this plate. Because usually when we get the donor bones for studies to our lab, these are full bones. Yeah, so they're not bones where they suffered from this fracture and have, in this particular point in time, this plate as an implant. No, we get the full bone without implant. Yeah, so we have to introduce the fracture and screw in the implant. So how do we simulate the fracture? The fracture was simply simulated by cutting out this wedge here out of the bone. You see it also in the presentation. This is the simulated fracture. Yeah. And then a surgeon was in the lab cutting this artificial fracture, screwing in the plate and embedding the sample in these embedding blocks here. And then you see the sample is gripped by two cups, aluminum cups, A1. We have a ball here, a sphere that allows for a change of inclination of this upper part. This is necessary. Otherwise, you would restrict the movement of this construct, yeah, and you have different other moments and forces you would not like to have. Yeah, so we have a sphere here to let it move freely. And up here there's the load cell, and the movement of the two parts was tracked with this motion tracking system. There are again 3 markers here on either side, but this is now a different one to the last study you have seen. Okay, and when you press on the sample, you get a force displacement curve like this. So in the beginning you have the usual linear elastic region, and then at some point in time the slope is dropping, and then here you have your first local maximum. This is it's very likely that this comes along with some fraction noises, with some and then here the force was rising again. Yeah, this is, as said already, a compression test where you have to think a little bit more about your maximum load or your ultimate load or your failure load, because imagine you compressing this. Yeah, the implant is already failing, but these two pieces come into contact and you can increase the force even more. Although everything is damaged already, everything has already failed, but you can increase the load more, and this is what is happening here at the end. Yeah, the load can be increased more and more and more and more and more, but the actual failure, so where the implant bone construct is failing, is here. And this point was determined by first putting a regression line into the linear region, and then reducing the slope of that line by 95%, moving down with it until you touch the first local maximum. Yeah? And this point was used. Yeah? So the local maximum in this shoulder region here was regarded as failure load. So the failure load was 400 and something Newton, not much. So a little bit more than 40 kilograms. And I think you can reach 40 kilograms quite easy when you fall on your wrist. So it's sensitive and you can get a secondary fracture easily. With respect to the elastic region, how was this slope determined here? Yeah, you see, well, I will go into this in detail later when we talk about data extraction, data evaluation. Yeah, so this is basically a regression line for the first linear region, and this linear region ends here, which gives the elastic limit. So that's the yield point, the yield limit where the start of damage and plastic deformation in the sample is. Yeah, so it's the start of plastic deformation. And the slope of that line is the stiffness. So much about boundary conditions. So important is, depending what you want to measure, material properties, structural properties, you have to think about your boundary conditions accordingly. More complicated is the material boundary conditions. Okay, we see that we have to measure physical quantities when doing such kind of experiments. So measuring force, displacement, strains, and therefore we need sensors. So the second chapter for today is sensors. What sensors are usually used when you do experiments on bone and implants? The first sensor I would like to show you is a very small one that is usually not well known, but it's really important because it's used later on for force measurement. And the sensor I'm talking about is the strain gauge. And it measures the quantity of strain in millimeter per millimeter. What does that mean? Yeah, you have a material point and a material point, or material well, you have a length, let's say, and the length is stretched by a certain deformation, and you divide this deformation by the original length, that's the strain. That's why millimeter per millimeter. Change in length divided by original length, millimeter by millimeter. And this can be done with these small pieces here. And the principle is that you have a wire in the substrate, and when you stretch the substrate, also the wire is stretched and is changing its electrical resistance. And I found a short and simple movie explaining that, and I would like to show you that right now. I think that can explain the principle better than I can do that. So the measuring grid are wires, basically. So it's glued on the surface of something, and this something is deforming. So the strain gauge is deforming with this piece and changing its resistance. And the resistance change can be measured by electrical means. And this is linearly linked with this K factor you have seen here with the strain. And the strain gauges come in different kinds of shapes and for all different kinds of applications. Yeah. Buy them from this company. Yeah. Okay, good. So to sum it up, basic principle is you have some piece, you glue the strain gauge on it. It's a very small device, so 3 by 3 millimeters, for example. And as the surface of this piece is deforming, also the strain gauge is deforming, changing its resistance, and you get the strain of that part exactly at this position. And this is used for those force sensors. So force is actually measured by strain. So imagine this is a load cell. This is screwed onto our testing machine. You apply some load and you get a force output in your machine. But what is happening in reality is inside there is a piece of metal, so a rod. And on this rod, there are strain gauges glued that deform with this rod, right? But the material properties of this rod is known. You know, for example, okay, this is steel. Yeah, you know also the cross-section area of that. So by knowing the strain measured by the strain gauges, knowing the stiffness or the material properties of this rod and the cross-section area, you can calculate the force that must have been applied on this rod. So after some calculation out of the strain measurement, you get a force reading. So force in our experiments is measured by strain. This is also an important piece of equipment for measuring displacement. This is a LVDT in short, a linear variable differential transformer. It is made by a hollow cylinder and with the rod that is moving in there, and you get a millimeter displacement reading, and you can measure displacements very precisely, yeah, with an accuracy of a micron with this system. And the measurement principle is you have in this hollow cylinder part, in this tube part, coils, and the coil number A is subjected to a current, yeah, and the inner piece, so the rod, is made from ferromagnetic part, and depending on its position, a current is inducted into two other coils, yeah, so coils B, and this is what you measure, yeah, so you measure the voltage of the coils B, and depending on the voltage you can know the position of the ferromagnetic core here, yeah, so this blue piece is sliding left and right, and you have a voltage reading here at B. And A is driven constantly with the current. Yeah, I will not go into details here. I'm not an electrical engineer, I'm a mechanical engineer, so if you have further questions on how these things are really working and such kinds, then you have to go to a different lecture. An important piece of equipment, and which is getting more and more important, is measuring displacements with DIC, so digital image correlation. What is this? This is basically a video, yeah, nothing else. So as depicted here, you have a specimen. The specimen is loaded, and you have a good camera that is watching closely what is happening on the surface of your specimen. Yeah, indicated here, there is a grid on the surface of the specimen. This is important because the specimen needs to have some kind of structure. So when it deforms, that you know that you see actually the deformation. So some kind of optical structure is necessary. And this is recorded with the camera. So this is the measurement. The measurement itself, quite easy, just recording with the camera. And afterwards, yeah, so what is written here, yeah, you can have even either one camera or two cameras. We have in our lab two cameras, so a stereo camera, and then you not only see the deformation in plane, but also you can track deformations out of plane, so in 3D space when you have two cameras. Just like eyes, you have two eyes, so you can track parts not only in plane but also in depth. It's the same principle here. And from this one or two video feeds, so one video feed from one camera, two video feeds from the stereo camera, you can calculate the displacement of these structures in space. These structures can either be markers you glue on the sample surface. I have some here. Yeah, I have a sample with markers here. So this is a glued on marker, and this can be tracked in 3D space, or you have a speckle pattern. That means you have a spray paint with dots, yeah, that are tracked. This is what is shown here. So the algorithm is then tracking, for example, this point over time in the image. Yeah. And when you know the size of a pixel in your image, then you know the actual displacement in space, in millimeters, for example. Yeah. And when you know the displacement field, what is this? This is the displacement of all the pixels in your video feed. Then you can calculate the strain. Yeah. So for example, you have 4 points A, B, C, D, and you know how they move in space over time. You can calculate the strain of the surface. Yeah, and then the unit is millimeter per millimeter. If you would like to know more, this is a lot of mathematics going on, then you can read these publications or go into other literature. In practice, what you do in your lab is you have your test setup, you have your specimen, and you set up your camera and watch closely what is going on, and you get an image series or a video feed, and then you apply your DIC algorithm, and then you can track the deformation. So what you see here is the initial position of the sample. That's the green one. Yeah, the sample is structured with some spray paint. You see that crystal structure here on the surface. This is necessary for the algorithm to track it. And in this position that is shown here, you see the grid deformed into the red state. Yeah, so each part, so each node of the green grid is now moved to the red state. So you know the deformation on the surface, and by taking the first derivative of this displacement field, you get the strain field. You know also the deformation of the sample itself, not only the movement, but the deformation of the sample on its surface. Yeah, and this system can be used to measure strains. Yeah, strains of the sample. Very useful, very, very useful. Yeah, next chapter. Okay, we have set up boundary conditions. The sample is in our testing machine. We mounted our sensors. We know how to measure force, displacement, and strain. And now we have to tell the machine what to do. Yeah? The machine needs to get commands from us to move and to load the sample. And this can be done with two strategies. And this is important. Look here, we have again our uni-actual setup, some specimen and some clamps. And when we think of the experiment, we have some force signal over time and some displacement signal over time. And we can now decide whether to tell the machine to create some displacement over time, or we tell the machine to create some force over time. And these are the two types of control. Yeah? So we can do a force controlled measurement. That means the force is the order to the machine, and the displacement is the output, so the response of the sample. Or the other way around, I can tell the machine to produce some displacement, so to move down, for example, 1 millimeter, and then the response of the sample is the reaction force. So these are the two types of control a machine can do. This f of t and u of t indicates that these signals are functions over time, right? So this is what we now look on. So these two prescribed quantities, u or f, how can they be shaped over time? So a very easy way is to create a ramp in force or a ramp in displacement. So you start in the beginning, the sample is unloaded, and then you say, please move down 1 millimeter in 1 second. Yeah? And then the machine is creating a ramp load. So in this case, u is prescribed, so the displacement is prescribed, and the displacement is increasing over time, and at the end, after 1 second, we have 1 millimeter. Yeah? That's the ramp load. Vice versa, the same thing can also go for force. So let's say you would like to have 1 Newton in 1 second. Yeah, so then the force signal is increasing over time. So after 1 second, you have 1 Newton. Quite simple. Other possibilities, you can hold your quantities, your displacement and force over time. So you tell the machine, please hold the displacement. Yeah. If you would like to track, for example, the force response, yeah, when the sample is relaxing, then when you hold the displacement, the force is dropping because the sample is relaxing. Then you can apply a step load. This is, for example, important when you do viscoelastic testing. Yeah, you apply step load, zack, in displacement, yeah, and then you record how the force is dropping, how the sample is relaxing too. And this follows a certain characteristic where you can extract viscoelastic properties, but this is not within this lecture. Then, imagine you would like to measure something different. Yeah, so when you think back, when you remember, for example, this experiment where we would like to measure the fracture load of this bone implant construct, here we applied a ramp load. So we push down, 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 down until we reached our failure load. But there are other questions that can be answered with mechanical tests. For example, you have a hip implant and you would like to determine how many load cycles or how many walking steps the patient can do until the hip implant is breaking. That's a fatigue question. Yeah, so the usual load case of a hip implant is the patient is walking over years, yeah, making millions of steps. And what happens from time to time is that the implant is suffering from fatigue and then breaking at some point in time. And the question can be asked, how many load cycles can the sample take? How many load cycles can the implant take until fracture? And therefore you need to apply a cyclic load case, right? To simulate those steps, this walking, this gait of the patient. Yeah, so you have a sinusoidal load application. Again, either in displacement or in force. Yeah, there are different flavors here. You can do a sinusoidal or this sawtooth shape, and also with increasing amplitude when you would like to simulate increasing load. This can come in handy in different applications. I think I will show you an example in a few minutes. And the machine can usually also produce some custom load case where you have in the beginning a ramp, then a hold, and then something else. Yeah, or even a completely arbitrary function over time can be also applied on the sample. Yeah, so how to choose this loading protocol? Yeah, it depends on the research question. Yeah, depending on what you would like to measure, actually, you have to choose your loading protocol accordingly. And you can do that with two strategies. Yeah, for example, you would like to make a certain constitutive effect visible. For example, if you remember back, these graphs we have seen in the last lecture, where the stiffness and yield load and ultimate stress of bone specimens are shown here, and here you have the material behavior depending on loading rate. These two experiments were done with a ramp load in the testing machine. Yeah, so here the scientists applied ramp load, and the stress, so the force divided by the cross-section area, was measured as a response in this way. Yeah, and also in compression. Here, the ramp had different slopes. Yeah, so the slope of the loading ramp indicates the speed of the test. Yeah, so for example, for this very slow test, the ramp was maybe something like this. Yeah, and for this fast test, the ramp looked maybe like that. Yeah, so this is a slow ramp, and this is a very fast ramp. And here different material properties were made visible. So the constitutive effect of viscoelasticity was made visible here by applying a ramp load with different slope, the different loading rate. So second example, this is the picture where we saw that bone is damaging when it starts to deform plastically. Damage is a decrease in stiffness. So the slope of this regression line is higher than this regression line, so the stiffness already decreased. And to make this visible, you have to unload and load again. Yeah. So for this experiment, to make damage, the constitutive effect of damage visible, you need to select your loading protocol accordingly. And here you need cyclic loading with increasing amplitude. So as shown here in the bottom. So the first cycle has this amplitude, the second cycle has this amplitude, and the third cycle has this amplitude. And this is what you have to do for making a graph like this here. This was the creep experiment. So where we have seen that depending on the applied stress that was held over time, the strain of the sample was increasing or not. Yeah? So for low stress states, the sample was staying at the same length, and for higher stress, the sample was creeping over time. And for measuring this, you have to apply a step load. Yeah? And a step load in stress, so in force here. So F was increased in a stepwise fashion and held over time. And the deformation was tracked and then transformed into strain. And this is what you see here. Second strategy, you would like to mimic a certain load case. So remember back to this accident, this fall of this lady. She was falling on her hip and on her wrist. In this case, we have to apply a fast ramp load. Yeah? So hit like this is nothing else than a ramp load in a very fast fashion. Zack. Either force or displacement controlled. This can be chosen more or less freely. Yeah? So when you know, okay, you would like to have a hit with a certain load, then you can apply a force. Or when you say, okay, I would like to go to fracture, yeah, until the bone fractures, you don't know at which force the bone is fracturing, then you apply a displacement at a certain very fast rate. Another example, as already indicated, walking. When you would like to mimic a walking load case, then you have to apply cyclic loading. Yeah, so this can be done very fast. So usually you have a walking rate of around 1 hertz, one full step cycle per second, or a bit faster. And this can be compressed into a faster regime. So imagine you're doing your tests not at 1 hertz but at 10 hertz. Yeah, then you have 1 steps per second simulated in your machine. This is an advantage of mechanical testing. That means you can compress a full life cycle of something that lasts for years into a shorter amount of time by increasing the frequency. Yeah? So the real gate cycle is maybe like this, step, step, step. But in the machine you can do it like that. Last chapter for today, data evaluation. Data evaluation. So what does this mean? When you do an experiment, usually the machine spits out a sheet like this. Yeah, it's a text file with the time signal, the displacement signal, so time signal, displacement signal, and force signal. So this is the very classic form of output. And so that you know maybe you've also heard of the CSV format. So it's a comma separated value format. It's a text file that is actually containing a table. So exactly something like this. The goal is now to extract material or structural parameters from this actual numerical data. The first step usually done is to make a plot to see it. Yeah? Here you see the displacement, so the center column over time, and the load, which is the right column over the time column. You see that it's a very complicated experiment. Thanks to Martin Frank for the data, but the type of experiment doesn't matter in this case here, yeah? Just to show that you first create a plot. If necessary for extracting material parameters, you can convert this force and displacement signal into stress and strain by dividing the measured force by some cross section and dividing the displacement by some initial length here. And then you get stress and strain. This is valid for small deformations as a disclaimer. These are the engineering stress and engineering strain measures. Yeah, and you get an additional sets of plot. Now we have strain over time and stress over time. We are already in the material regime. And then we can extract, for example, stiffness values. In the case of structural properties, it's really stiffness, so K. And in case when we are in the stress and strain regime, it's the Young's modulus we are extracting. And we need to get the slope of the linear elastic region of our experiment. The issue is that usually real tests look like this, so very bumpy and noisy signals. And the question is, okay, where is now the linear elastic region, and where is the slope of that linear elastic region, which is needed for stiffness or Young's modulus? And there are different possibilities, but in general we would like to use a strategy that is consistent and can be used consistently for a study. So imagine you have 10 samples, and you would like to extract Young's modulus of these 10 samples in a consistent way all the time. Yeah, what you can do is, as the very first possibility, you can take the initial slope. Yeah? So the slope of the first two data points, so the data points are indicated here by this point line, yeah? And you just connect the first two data points, and this is the slope. But in this case, it's not fitting very well because this slope here is not representing the rest of the curve here. Yeah, it does not mean it's wrong. It's just a strategy. Yeah, you can say, okay, I'm using the initial slope method for extracting my stiffness values. Or what you can do is you can walk through these data points, yeah, and note the slope between 2 points all the time. Yeah, you say, okay, these 2 points have a slope like this, the next 2 points slope like this, next 2 points slope like this, and you note down the slope all the time. And then you select the maximum slope, yeah, you have measured. And here in this case, in this example, the maximum slope occurs here, somewhere here, and this would be now your stiffness or Young's modulus. And you see there's already a huge difference here when you have test data like this. Yeah? Depending on the strategy, your values are. Your values are also different. And as the last method, which is a little bit more sophisticated, you use the best linear fit. So you take a line which is straight and say, okay, in which region is the line fitting best to the test data? And this is also called the R-squared value, the R-squared method, because the R-squared value, so the coefficient of determination, is indicating how well the regression line is fitting the data. Yeah? If the R-squared values is close to 1 or even 1, that means that the test data is very linear. And if the R-squared values is low, close to 0, then there is no linearity at all present in your test data. So what you can do now is you can take your line, yeah, and put the line in a certain window of your test data. Yeah, so imagine you consider only this region of test data and put a line there, yeah, and you measure the R² value, so how well it fits. Okay, then in the next step you increase your window, yeah, and make it larger, and put the line in there and measure the R² value, yeah, determine the R² value, and you do that step by step until the end of your test data. Yeah, and you have for each window size an R² value, and then in the end you select this window with the maximum R² value, so with the best fit, and this is indicated here with this green box. This is the window where, when you put a line, you have the best linear fit. And what you get out then, if you put in the line there, is this slope. Yeah, this is the best linear fit in this window. And you see that is actually in this case the best representation of the data. It doesn't mean that it is correct or that it is not correct. It's just another more sophisticated method that is used by our group quite often to have a consistent way for bumpy curves to determine the slope. Other methods are also possible. Second question. Okay, how to determine ultimate load in the case of structural properties, or the strength, so the ultimate stress in the case of material properties. Again, we have a real curve, so with bumps and all different kinds of kinks, and we would like to have a consistent method. Possibilities are: simply take the maximum value of your curve and you are fine. As stated before, this can be problematic in compression tests, because then you can increase the force or the stress even more and more and more and more, and there is no real maximum, as seen here when you remember back the experiments with this distal radius. Then you have to find a local maximum that ideally goes along with some cracking noise, so with some other indications of failure at this point. Yeah, so either take the max value or a local maximum value for your ultimate load. Yield load or yield stress. So that's the point where the first plastic deformation occurs. Yeah, that's the point where, when you unload the sample again, some remaining deformation is still in place. That's the limit of the elastic region. Yeah. And this is very important to determine, because this is in practice often the range in which it is allowed to load an implant, for example. You don't want the implant to deform plastically. You would like to keep it in an elastic regime. So then the yield load is your limit, or the yield stress is your limit. And the problem is that for bone, there is no real distinct elastic limit. It's rather a transition zone. So for example, when we say this is a test on bone, then here, somewhere here in this region, the bone is transforming from elastic deformation to plastic deformation. Yeah. But still, we need some consistent method to determine some point. We need to report in our report some numerical value for the yield load or yield stress. So one good method is to use the right border of our window of our R² method. Yeah? Remember back, we were determining the slope of the linear part by this optimization method where we increased our data window, and at the point where we have the best fit, we have a certain data window size and the right border here is the elastic limit, and the stress here is our yield stress, or the force here is our yield load. That's the first possibility. Another possibility is taken for testing aluminum. Aluminum has also no distinct yield point, and what is done here usually, you take a parallel line. Let me delete those things first. You first determine the slope of the curve, with some method, and then you take a parallel line and make it intersect with the 0.2% strain value. So in this case, forget the U here. We are just looking on strain now. So this method is only valid for strain measure, so stress and strain measurements. And we make a parallel line through this 0.002 value here. And then we intersect this line with our measurement curve, and we end up here. And then this is our yield stress. This is a method taken from aluminum measurements, and this can be also applied and is applied on measurements on bone. Why not? Other possibilities are also there, etc., etc., etc. As the last step for today, I would like to show you an actual data evaluation. We see here the three columns of our test data, so time, displacement and force, and the first step I recommend is to create a plot. So let's select all the displacement and force values. I know there is some shortcut, but I don't know it, so I have to do it by hand. Okay, and then we insert a scatter plot. So let's move up and place it here. So this is our force over displacement plot. Let's insert some not data labels, axis titles. So here we have on the x-axis it's displacement U in millimeters. On the y-axis we have force F in newtons. Okay, and we would like to extract two properties, namely maximum force, so ultimate load, and stiffness. First, the easy thing is ultimate load. The ultimate load here is really the last point here, because you see that there was some fracture occurring. I think this was a tensile test. So here the load was applied, tuck, 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 and at some point in time the sample was rupturing in two pieces and the force dropped to zero, like this. And this is our ultimate load here. And to find that value out, this is easy. We make a formula in Excel, max, and we say, okay, give me the maximum force. And it should be 12,456 newtons. Can I select this here? And you see it in the small window here, 12,456 newtons. That's our ultimate load, or maximum force. Okay, the next question is the stiffness of the sample. So we somehow need to determine the slope of this region here. It's quite linear. There's some small bump here could be the case just from looking at it that it is somehow bent that way. Yeah, that means that the slope is decreasing over time. And what can we do here? I would now apply the method of maximum slope. Yeah, so let's find out the maximum slope in this region here and take this as our stiffness value. So first I would like to determine the slope between the data points at all, yeah, to have a resource for determining the maximum slope. So for this I'm calculating the so-called differential quotient. So diff which is basically the slope between two data points. So what is this? This is the change in force between two data points divided by the change in displacement between the two data points. You've learned this in high school, so please, if you don't know that now, please remember that. So change in force divided by change of displacement. This is our differential quotient. And I will calculate this now for some region here. Let's say until 1.8 millimeters or something. So I'm copying that down. You see in the center column, I'm now at 1 millimeter. So let's stop. So go until 2000 points. I think that's a good border. 2000, line 2000. Okay. Yeah. So these is the slope between all the data points, and let's plot this. So let's add an additional series. Series name diff quotient. X values is displacement, but we go until the cell 2000, and the y values are the differential quotient, and we go also till to 2000. Yeah, just to make sure, was this done? No. Excel is very, very buggy, even after 30 years of development. So edit, now it was taken. Okay, good. Okay. Oh, and we see, yeah, in orange now our slope values. Yeah, and we see that we have a high peak in the beginning. There was something happening in the beginning. So these are the two values, something times 10 to the power of 5. This is very high. So let's delete this, and now we see a more realistic picture. So we see that is now the slope of our data curve between all the pairs of data points. Yeah, we see a slight decrease over time. There is some drop here. You see a flat spot here, and this is indicated by this drop of slope, and this goes on. Yeah. The thing is now, when we determine now the maximum slope, so we take the maximum value of the differential quotient, we would get this slope here at this point. This is very early in the test series, so something need to be aligned already here. So I would not really take this value, but rather take the maximum slope in the rest of the differential quotient data. Yeah. So what I do now is I delete even more values, yeah, until this first peak is gone. Yeah. So here. And to get rid of this initial alignment phase of the sample. Yeah, this seems to be a little bit unrealistic. And now this is it, and I take now the maximum value again of my differential quotient column, maximum of D. Yeah? And this is this value. So this is maybe the value of the orange curve, something like here. Is this, or here, 7. So somewhere here. Yeah. So this is the maximum slope of the blue line. And now let's check how good our determined stiffness is representing the data. So let's create a line, yeah? So a regression line for our data to make it visible. So which is this? The regression line is a linear function with the slope of the stiffness. But let's take these dollar signs to keep it at this position, times the displacement value. This is are the line points. Let's check if it's taking the correct values. Yeah, it's always the stiffness times the deformation, and we can copy this line values down here. And we add this line data as an additional data series. Add, we call it line. X values is again the standard travel till data point 2000. Y value is the line data, also till 2000. So okay, witness me, I'm pressing on OK, but it was not taken. Thank you, Microsoft. Now it was taken. Okay, and we see it. That's our gray line now. This is our regression line with the slope of our determined stiffness. And it's not so bad. It's representing rather the slope here in the beginning, but it's totally fine. As we see in the orange curve, the slope is decreasing, and we use here some, or the maximum value of that orange plot is somewhere here in the beginning, maybe here, and that's fine. But we found a way to determine that slope and determine the maximum force. And this is the structural properties we wanted to extract out of this test data. So maximum force 12,000 and something Newton, and the stiffness is 7.24 to the power of 3 Newtons per millimeter. And we are done with our data evaluation. That's it for today. I hope you found it interesting. See you the next time. Bye.